5.6, integration with exponentials and logarithms. We've mentioned some of these things already, but there are some particular formulas here you want to be well aware of. Okay. We've already mentioned that the antiderivative of e to the x is, of course, itself. And we also mentioned earlier that the antiderivative of 1 on x is related to the natural log. It's the natural log of the absolute value of x. So this is the only power function, right? It's x to the negative first, really. This is the only power function that does not obey the reverse power rule, but is specifically evaluated with ln x as its antiderivative. Okay? And its absolute value, again, I mentioned before, so it widens the domain of the natural log function. The natural log function would normally have a domain of greater than 0, but once I put the absolute value on here, on the independent variable x, it allows the x values to not just be greater than 0, but also less than 0 as long as they're not 0 exactly. So it basically doubles the size of the domain that's allowed here. Yeah, that's really all it's doing. Now, so that gives us the idea of what to do when I have the exponential inside and how I get the logarithm as a result. It doesn't tell me what to do with the logarithm on the inside, which is much more complicated. The book is kind enough to give us a formula for it, right? Even though the methodology to perhaps derive that formula isn't within our grasp at this stage in the textbook. But nevertheless, an important formula to be aware of now is what happens when you have the natural log itself as the integrand. Okay, so it turns out, again, just telling you as a formula, it'll be x ln x minus x. Okay? So there's the essential formula when you have a natural log inside an integral. And even though we didn't really derive that this was the case, you can easily prove it to yourself by taking the derivative of this expression, and you will achieve the integrand. So therefore, if I differentiate this, I get the integrand. It must be the antiderivative of the integrand was the original function here. So let's just take the derivative real quick to prove it to ourselves, and we should have a product rule here. So I have first times the derivative of the second plus the second times the derivative of the first, which doesn't need anything done, and then minus the derivative of x here is 1, of course. But x on x here is 1 for all legitimate x values for this expression. So x on x is 1, 1 minus 1 is 0, so I just end up with ln x as expected here. So therefore we see this is a correct antiderivative for the natural log function. The rest of the section is just devoted to combinations of these things inside more and more complicated integrals.